very heartily welcome to everyone from Liestal, close to Basel in Switzerland. Today I want to present the Alphacen 300 system to you. It's our latest system for large and heavy samples. But before we go into the system itself, maybe let me quickly go a bit into history. So Nanosurf is actually the market leader for customized systems, our AFM systems, and we have quite a strong international track record with these products. I'll show you like a few systems now. What you see there on the screen right now in the bottom left is a rather small customized system. It's for samples of 240 by 240 millimeters. Also, this one has a vacuum chuck capabilities, and this is a rather compact system. Samples could be a few kilos. We also do stages for much larger samples. So the stage for, or the sample for this stage was made for, is like more than half a meter wide and 1.5 meters long, and weighs around 500 kilograms. So this is quite a difference, and not that easy to do AFM on such a sample. But we also do systems for smaller samples, like this is 0.5 meter diameter sample, round sample. The special thing about this stage is that all the translation mechanics is at the bottom. It's below the sample, so that nothing can fall onto the sample from on top. There's no real movable part except for the AFM scanner, which is sitting on top of the sample. This stage also has a rotation stage, so you can rotate your sample by 360 degrees to address the sample from different viewing angles. This said, you see that we did quite a bit of stages already for differently sized samples, but what we were lacking so far was a standard product for samples in the size of, or up to 300 millimeters, so 12-inch wafers. So what you can see here on the screen is the Alphacen system as it would come or would be delivered, except for maybe the table, typically. On the right-hand side here, you see the Alphacen system. That's a composite of table, stage, acoustic enclosure. And you see on the left-hand side, the control station. In the bottom or below the table, you see there is the AFM controller in a rack. It's on top. Below that, there is we call it Alphacen controller, which includes the stage controller, but also has a vacuum pump and a pressure pump to allow using a vacuum chuck and to move the table. And it has also built in the controller for the active damping, vibration isolation, and the PC. So the system is made for 300 by 300 millimeter samples. So the sample platform has this size and is fully accessible, and it's motorized. The sample can weigh up to 45 kilogram, and to reach that weight on the sample stage is quite difficult. You would have to use a massive lead sample of approximately 300 by 300 by 35 millimeters or so to really get to the limit of this weight. So you can really think that most of the samples you can easily load on that. And this is much more than you can typically load on other stages where you use the stage as a scanner. Okay, that said, who's in need for example, for such a stage? There is typical samples that can be observed or investigated with such a setup. Of course, there's optical lenses or glass lenses that can sometimes be relatively big. Gratings for different applications. Mirrors, could be glass or metallic mirrors, but also holographic structures, and of course, wafer structures, so silicon wafers, but whatever, glass wafers, silicon nitride wafers, all these kind of things. And typical applications, what people use the AFM for when they look at these kind of samples is, of course, just simple surface topography, They want to know how rough their surface is, for example, after polishing process or treatment process. For gratings, they typically look at some properties like periodicity, depth of the grating structure of the trenches, sidewall angles, things like that. But also for process control, like etching, after etching, coating, applying a coating, or cleaning the sample, one wants to know if everything is all right, if the previous process has been done correctly, so that in a multi-process sequence, then the next step can be started. So the system was designed to perform low noise measurements, because for the surface roughness, especially of wafers or optics, the surface roughness has to be typically small, and you need to have a low noise measurement in order to get these small roughnesses measured. So what do we do to get there? We took care that that in our system we have our latest controller included, which is a very low noise and high bandwidth controller. To our knowledge, it's the lowest noise controller currently on the market. We also take care that the scan head has a very low noise superluminescent diode light source, which is working in the near-infrared wavelength regime. We took care that the stage itself is robust and designed in a way so that you don't get vibrations because of the floppy structures of the stage, so this is very rigid. And we also use an active anti-vibration system that to damp out vibrations coming from the floor into the system. To improve the shielding to acoustic noise, we have a built-in acoustic enclosure, or built around, let's say, this big black box that you see on the right is the acoustic enclosure, and the whole stage is resting on a stable supporting frame to which also the anti-vibration isolation is mounted. Okay, so examples. So there is an image, for example, here of a fused silica glass surface or fused silica surface, which has a roughness of around 112 picometer RMS or RQ. And if you look at the RA value, that corresponds to 87 picometers, which is quite a smooth surface already. Another example is a silicon carbide sample where you see steps of or layers of the silicon carbide in terraces, and the distance between two of these layers or terraces is 1.5 nanometers. And sometimes here you see also there is some smaller terraces here and here. These are half steps, and they are around 0.75 nanometers steps that you can find here. So what else do we do to make this system special and well suited for large and especially heavy samples? We use a tip scanner. So the advantage of a tip scanner is that only the tip is scanned in X, Y, and Z, in contrast to sample scanners where the sample is scanned at least in X and Y. If you now load a lot of mass onto such a sample scanner, then the performance because of the loaded mass decreases at some point. And this is not the case with a tip scanner. And this way you can have a small sample, a wide sample, but also wide and thick, so meaning heavy sample that you can investigate with the AFM without compromising on the performance of the scanner itself. And just to remind you, I mean, like a 300 millimeter diameter and 6 millimeter thick piece of fused silica glass is already like a kilogram. And that for most sample scanning AFMs would be already a no-go. What else do? We took care of the translation mechanism. For such heavy samples, you have to make sure that you can move them around in an efficient way. So we use air bearings that allow basically to move the sample on a small air cushion and thus virtually frictionless. We also make sure using this air bearing technique that once we rest the sample after positioning it, it has a stable support during the measurement. And also the translation mechanics itself is not part of the mechanical measurement loop during a measurement. And this way, it cannot add noise to the measurement. We also have a security out mechanism that allows to give some security while moving the sample or moving the stage, for example, manually, and to prevent a hard crash between the scan head and the sample, thus preventing both the sample and the scan head from damage. So we put some focus on ease of use. We have a tool that allows you to have where's my mouse gone? Here. To have a representation of the stage sample platform. The blue circles indicate distances from the center, and you can, then we see that later, you can click on a certain position, move to that position, but you can also tell you want to go to a sample exchange position or cantilever exchange position. Furthermore, we have, you can automatically acquire data. We have a batch manager, and this you can operate in different ways. You can either move the sample at the stage to a desired position, save this position, and take then later on an image there after defining several of these positions, or you can feed a list of positions if you know where your samples are located into this batch manager, and then run this list of measurements. You can, on top of that, you can also use our scripting interface to do more at a different position. So the batch manager by default would do a measurement at a single location with a given, let's say, size, or with a given mode. You could change that by scripting so that you can, you could do at a one location multiple things, take images of different locations, things like that. So as you saw, we can use quite big samples, but sometimes you also may still have a small sample. And so this is also possible to use small samples on the system. You can use our cantilever hold or sample holder line up here, which is basically here the standard sample holder to just mount a small sample on a small sample chuck, for example. But you could also extend the range of measurements that you can do with your sample, for example, by having the C-AFM sample holder, which has a preamplifier built in to measure low current through the tip if you have a conductive sample. But you could also use the heater to heat the small sample up to 250 degrees, or the heater and cooler to cool it down, but also heat it up just to 180 degrees. And you could even use the environmental control chamber, which would allow you to cool the sample much further, because you can work in an environment in which you have, for example, a nitrogen environment which is dry. And you could also use, for example, the EC cell, which is also compatible with the stage, and you can do electrochemical experiments. With most of these sample holders, however, the range of that range that you can actually use and the size of the samples are restricted, just because, for example, for the EC cell, the electrochemical bath is rather small. But nevertheless, you can use it, and with a defined positioning, you also know where within your stage position this opening here would be, so that you can go down and do your experiment there. Okay, what else could be added to such a system? Of course, if you think about wafers, you think about a vacuum chuck to basically clamp the sample to the sample platform. But the sample platform could also be exchanged for one where you have a kinematic mount for the sample holders, for example. We're currently working on a automated cantilever holder exchange. So this is a tool where you can go to a certain position. You can drop your cantilever holder in an array, and from this array you can also pick up a new cantilever holder with an already mounted cantilever. And this way you can change the cantilever if it's picked up a contamination, or if it for whatever reason got blunt or contaminated. And you could do that also remotely, so you don't even have to be at that position at the system, or you could, with the scripting, also address it that this is done after whatever 50, 100 images. Furthermore, we are currently building up the capability to manufacture the stage so that it's suited for clean rooms. Something like an ISO 6 clean room, we could provide a system for in our facilities then. So this is optional features that are rather standard, but then you could also think, okay, I have something which you don't have. So as we're coming from customizing, also there's possibilities for the Alphacen 300 to do modifications, also go beyond the Alphacen 300 if that's necessary. So what would this include? For example, you can have vacuum chucks, different vacuum chucks. You can have, as I said, kinematic mounts for our sample holders, or you can have a transfer sample holder that allows you to have a sample, for example, on an optical microscope, investigate it optically, then figure out there's a defect at a certain position, move that sample back to the AFM, and then know where this defect has been or where to find this defect. If you have specific requirements for a sample to be mounted, this could also be taken care of. If your samples are larger than 300 millimeters, there's ways to increase the stage. The stage is made to be scalable. If you need or would like to have some stage like that just for small samples, there's also a possibility. And so also one thing that sometimes comes up, or that often comes up, is the question about how safe is my sample and how safe is the AFM. So there's also possibilities to increase the safety measures. You can have forbidden areas of your stage, for example, where the cantilever should not go, or that the AFM should not go or should not move to. You can have a sequence of motion so that you always go in a safe direction when you move the stage. You can have photoelectric barriers or proximity sensors or interlocks. So there's different ways that one can customize a system more for security if you have especially precious samples or something which goes through many processes, and damaging this would be very, very harmful. Okay, so much about like a PowerPoint presentation. I will just show you what we still do in the rest of the time. We will have a look at how to operate the AFM, how the stage is being moved, what possibilities there are to move the stage, what cameras we have, how you can observe your samples. And then finally, we will do an image of silicon carbide with these 1.5 nanometer steps. Okay, so I just stopped sharing my screen, and I switch over to another camera. Now what you're seeing here now is the camera still looking for the focus. This is the acoustic enclosure of the Alphacen system. So it has, you can see it has a large front door, which is made to allow you easy access towards the sample. It also has another door at the side, which sometimes is also very nice to go there and to handle the sample. Yeah. So components of the system. So we have the AFM scan head sitting here. It's mounted on a Z stage, a 50 millimeter Z stage, and we have the 300 millimeter sample platform down here, and this can be moved on this granite plate. So what you can also maybe see is there is a camera in the door, which is sitting here, and there's another camera in the here in the side wall of the acoustic enclosure, and we will come to that in a second. We also put some illumination in the chamber that allows you to also, when the door is closed, to make use of these cameras.
The front camera isn't in view if you just want to close the door slightly.
So yeah, sorry, I didn't see that screen was. So the front camera is, it's just sitting here. Okay. Yeah, so maybe I can quickly demonstrate and the PowerPoint, demonstrate the loading and cantilever change positions. So you can have this tool. You can say you have a sample change position. So you can see that the stage, I reduced the speed, unfortunately, that the stage is slowly moving to the front. And unfortunately, we have to wait until this is done. Yeah, but then once the stage is in the front, you have a nice access to the sample platform and can mount the sample, can take out a sample, handle a sample, manipulate it, do things like that. And similarly, we have a position for cantilever changing. So the cantilever is held on a holder below here, and the cantilever change position would be in the back corner so that you have easy access to the cantilever holder without touching your sample. Okay. Good. So now it's moving back to the original position. That also unfortunately takes a little. I should have changed the speed beforehand. Yeah, you have to wait for a moment. Okay, but what else can I show you in the meantime? Let's just share my screen again. We have the possibility to make use of these two cameras. And now when I close the door, you can see both of the cameras. The one on the left-hand side of the screen is looking from the side, and the one from the front is on the right-hand side of the screen. And you can see that you can now see the sample coming below the cantilever holder, and this nicely gives you an idea of how far away you are from the surface. So if you want to approach manually, so this is that tool. Just close that. Just a second. If you want to approach manually, you can observe how far you are away from the surface. So I can show you as an example. So we can move up and down, and you can relatively well see how far you're off the surface. But you can also position a small sample, especially if you have a small sample, you can nicely position it below the cantilever. So which possibilities do we have to move the stage? I showed you this one thing here already, where we get to the sample exchange position, but we could also say, okay, let's go more or less to the center position and say move stage to this position. Now in the other video you see that this was moving. So now we are above a smaller sample that I was putting in the center of the stage. Apart from this tool, you have also the possibility to use the stage control buttons to move the stage in X and Y, but also in Z. You can change the speed. That's sometimes important if you have small samples or you want to address a certain position exactly. But you can also say, if you know that you want to go to a certain position of the stage, that you want to go to a position, whatever is it, 250 millimeters, and this would be 150 millimeters, and say move to that position. And then you see also here the stage is moving, and there should come up another sample that I just put in for reference. So if you have known positions, you can easily address them. And if you now want to do a sequence of images, what you could do is you could say, use the batch manager and say, okay, I have my sample at this position. So add this to the batch manager, and then you add this position. And you could do that for a number of positions, and this way build up a list of positions or samples that you want to measure in a sequence. Yeah, without basically being around, you could just hit the button and basically go and wait until the measurement is done. Yeah, I think the next thing I would like to show is the measurement of the next sample, of the sample. So I just move there. And okay, we can close this. And now we move towards the surface. So now I'm very close already. You can see here, there's the side view of the camera from the AFM. You can see at a 45-degree angle the AFM cantilever, and this is the AFM cantilever from top. Now I'm already very close. To do a coarse approach, I would reduce the speed a little. And now, since the sample is quite transparent and I don't see a proper shadow of the cantilever on the surface, I would rather stop here and do a standard approach. So the way the approach will be done is that the Z piezo of the stage extends, and if you don't find the surface while doing this kind of ramp, the stage will move the scanner a little down and then repeat that step until we find the surface.
So, Christian, maybe during the approach, we have a first question, which is, I could hear some clicking and hissing noise. Can you say what that is?
Yeah, so there is two sources of noise that come up when you move the stage. The first one is that we need to apply a pressurized air in order to form this air cushion below the with the air bearings, so that we can move the sample while it's floating on this air cushion. And there's valves that allow, or that basically are triggered, and to apply the pressure and to release the pressure or pressurized air. And this starts, of course, the valve clicks to start to apply the pressurized air, and then it closes to basically set the sample down on the stage. And then there's a second thing that we probably didn't hear now, but if you would have the closure open, you would hear that there is also a clicking when the Z stage moves, and that's the brake that makes sure that the stage does not move further once it has done its small motion. There's a brake that clamps the stage in this position to have a stable Z position. Yeah, is that sufficient?
Yes, I guess it is. No follow-up so far.
Okay, so what I like to do once I approach from far away, I just do a second approach just to make sure that the drive frequency and drive amplitude are correct for what I want to have as a desired vibration amplitude. So that's done here. And now let's just see, it was a random position I went to. So let's see if we have some. So that in the background was the image from this morning. So just erase that. And what you can see here now is as you see here in the image already, that there's kind of steps. So you see that in the color gradient that there are steps. And you can also see down here in the line graph, which always shows you the just scanned line, that there's also this kind of staircase. And this is exactly these steps of the layers of the silicon carbide. For people that are maybe in industry, which is a nice thing that we have, an optional feature is a software to, what we often like to offer is a software called a Mountains SBIP or Mountains Map, which allows you to post-process your data. And the nice thing about that one is that you have a full track record of what you did to your data. You start off with the loaded data. You can have multiple channels in here, of course, and here you would extract one channel. And what I did here is I was doing a line by line fit. And then since these layers are a bit tilted towards the surface, what I applied is a plane fit, but I wasn't using the whole image as a plane. I defined the plane on one of these terraces, and this way you make this terrace flat, and since they're all parallel, you get these nice staircases. And if you then draw a histogram of this image height histogram, you get these nice peaks for each of these terraces. And then if you measure these 10, here I think it's 10 steps that I measured, you end up with a 1.5 nanometers per step. And what you could also do then, for example, in this software, you could extract a single of these, the surface of a single terrace, and then apply a roughness measurement to this single plane, and then you would end up with something like 90 picometers for this surface here, which is basically what the manufacturer of the sample also specifies as a surface roughness of on these terraces. Yeah, maybe have a look how far the image is. Yeah, we're almost done. You can see there also, yeah, Daniel?
Yeah, so actually you were speaking of industry, got a question, what's the learning curve for using this system or a system like this? Is it hard to learn or is it pretty straightforward?
I think it's rather easy to learn. So the basic operation is rather simple, just to the way to get an image and to acquire an image. Talking about industry, where you maybe want to think about less experienced AFM users or technicians that should do the experiment, or if it's a standardized experiment that you have the same kind of sample coming back to you over and over, you could also save the settings that you need for a certain sample. We call that parameters, like the amplitude that you're using, or the set points or the scan sizes that you want to have. You could save these as parameters, and you could just simply load them again. And so then it's very easy to apply these measurements. And you can have then a set of parameter files for different samples, different conditions, things like that. Okay. So relatively easy to learn. And you could also include that into a script for the batch manager, so that at different positions, or if you have multiple samples, not just one big sample, but several small samples, that you apply the settings for each and every sample. You have different settings if possible, if you need to do that.
I hope that answers the question.
Okay. Yeah, so the image is done. I would typically withdraw, go to another sample, and go on with the next measurement. So, but I think for now, I think that's most of what I wanted to show. Yeah, so I guess I'm open to more questions if there are.
So the first question is, did I understand correctly that I can measure multiple samples or locations on a large sample in a fully automated way using the batch manager?
Yeah, that is true. So you can define, so there's different ways to define how you do it. Either you mount the sample somewhere on your stage, and then you move to the sample, initially define this position or save this position. Then you move to the next sample, define a position, and you do that for all the samples that you have. And then you just run the batch manager, and then it measures all the areas that you want to measure, or the samples that you want to measure in a sequence, basically without your interference. And the other thing that you could do, if you define the positions more or less accurately, it could be that you have a sample platform which has dedicated spots, and you know the positions already. You could just upload a list of positions that you want to address. So then you don't have to go to each of these positions. Initially, you can just upload a list and then run the batch manager and also do the measurements. Yeah, in an automated fashion.
I hope that answered the question. Sounds like a pretty sophisticated system. Next question would be, what program language? Well, that's actually a follow-up. So what program language does the batch manager use, and is it difficult to learn?
To set up the batch manager?
Yeah, I think so.
So in the simplest way, there is already a script behind the batch manager which would address all the motion and the scanning. And in the simplest way, it would scan all the samples with the parameters that you have right now on the screen. With the scripting, you can adapt that. You can have different conditions for each position, or multiple conditions at a single position, meaning different sizes, different scan angles, things like that. What we use here as a scripting language is typically a Visual Basic, so it's not that hard to learn. But you could also interface with, if you want, you could also interface the whole system with Python or C++, if that is a bit more what you're used to.
Okay, thanks. Sounds good. Next question is sort of similar. What's the learning curve for using the Alphacen system? So thinking of industry people with no actual AFM experience, is it easy for them to learn to just use it, or do they have to take long educational classes or so?
Yeah, what we see is typically that it's rather straightforward to use it, especially if you can set up procedures. I mean, for example, for different samples, you can set up parameter files that define the gain that you should use, the amplitude that you should use, or the image size that you want to acquire. And you can load these parameter files in the software, and you could also in the script define, let's say, if you have different samples that, for example, you have a grading of different step height or different periodicity, you can also define that, for example, via scripting. So in general, you could prepare these scripts or these parameter files, and then could let somebody that has less experience run the system. Placing the cantilevers is rather straightforward. We have an alignment structure in the cantilever so that the cantilever typically ends up in very much the spot, if you change it, that the previous cantilever has been. So laser alignment is highly facilitated there. And yeah, as long as it's a standard imaging application, it's rather a steep learning curve, yeah.
Right, sounds good. Next question. Can you keep the door open during scanning so that maybe we can add an extra lamp to adjust lighting to see the sample better?
Yeah, I mean, you could of course keep the door open, but that of course compromises your acoustic enclosure or your acoustic damping capabilities. There is actually plenty of space inside the Alphacen, so you could even think of mounting something inside or to the wall. Yeah, it depends on how big this lamp should be. I mean, actually, we have LED stripes installed inside the box to allow illumination of the sample, and then, yeah, depending on where you place them, it might be better or worse for your sample. That has to be tested. I guess it depends a bit on a sample to sample. If it's a glass, if it's a piece of metal, yeah.
Okay. Is the stage air floated?
Yes, as long as it's moving. So the whole stage, you mean? Okay, so the sample platform is air floated kind of while it's moving. That's the air bearings. The stage itself is not. It's on a solid table, and the granite stage itself is damped via a active vibration isolation from a Curion. So between the stage, actually granite stage, and the table, you have the active vibration isolation.
Okay, good. Next question. What is the maximum scan size in X, Y, and Z?
Yeah. XY is 100 by 100, and Z is 10 micrometers. Yeah, one thing that I forgot to show and to explain is maybe we can show the camera.
Just close off my video to not distract.
Yeah, just a second. Yeah, it's a feature because it's just sitting on my desk. I kind of forget about it. It's this thing here. This is an emergency stop. Oop. So this is an emergency stop button. So if you tell the stage to move somewhere and you didn't take care of the shape of your sample, or if you have multiple samples on there, you can basically hit the button and the stage will automatically stop moving. And you also have this key here so that you can basically take away the key, and then the stage is non-functional. So if you want to make sure that no one is using the stage while you are not around, you can just turn it off. And if you are in the emergency stop case and you trigger the emergency stop, you also need to move away from that position probably. And for that, you have an override button here on that control that allows you to override the emergency stop and move your stage into a safe position. Also, we have included in the system, we're monitoring the deflection signal, or not the light that is coming back from the cantilever towards the photodetector. And if you would move, let's say you manually approach the sample and you have a glass sample and you don't see the surface, or don't see a shadow on the surface, and you keep on moving, what may happen is that the cantilever touches the surface and keeps bending. And at some point, the light on the photodetector will decrease. And in that case, also an emergency stop is triggered. And to get out of that, you also need this security override to move backwards. So then you can only move in one safe direction. But this way, what you do is you maybe damage your cantilever a little, but what you don't do is you don't crash the scan head or the cantilever holder into the sample, and this way you prevent damage to your sample and to your scan head.
As you said at the beginning of the presentation, it would take a huge lead sample to actually get close to the maximum.
Yep.
So someone's wondering, what are the practical limits in the weight? Is there anything that would actually reach the limit or get over the limit? Are there real life samples that one might want to measure that get close?
As I said, it's I think most samples, if you're talking about silicon stuff, I mean, silicon wafers are anyway rather flat, so or thin, so they will not reach that sample. It's more the glass samples, but with the density of most kinds of glass that you have, you will never ever reach with the dimensions that you can use on that stage. You will never ever reach the 45 kilograms. If you're using metallic samples, large metallic samples, you may get closer. But as said, I mean, lead or silver. I mean, for silver, I think it's something like a 37, 38 millimeter thick silver block of 300 by 300 millimeters that you would need to put on there to reach that maximum. And yeah, I guess practically there's the stage is made for strong enough to carry anything that you put on it.
Okay, so you could really say it's a limitless weight.
Yeah.